Hey AP, this video is on calculating molar quantities. So in this video, there's going to be some things that are review, like hydrate calculations and combustion calculations, but then other things that are newer. So we're going to go through a lot of examples with these. I'm going to try to do an example of each type. If we get to example and you know how to do it, and you want to just hit pause, cruise through it, check your answer with mine, and then go on, that's totally fine. So for this one, watch what you need to watch. And then check your answers with what you need to check your answers on. And for some, it'll be longer and others shorter. So I'm just going to start plugging through these. So we have our mole conversions, right? This is the same diagram that you've seen many times before. The thing that's new on this is that we have to get between moles and volume. Up until this point, we've only used our 22.4 liters per mole, which is our molar volume. And this is only for gases. Okay, so I have that here and here. So this is gases only, because we used to only be able to go to volume for gases. But we know about molarity, which is moles per liter. So that means if I have a solution, an aqueous solution, I can also get to moles and volume. So same thing here. So that part's new, and we use it just like any other conversion, where we drop our units down, liters on the bottom if we're starting with liters, or we flip this over and put moles on the bottom if we're starting with moles. And we'll practice that in this first one here. So you will need a calculator and your periodic table to go along with these notes. All right, example. Some metals will react vigorously with acids to produce hydrogen gas. What mass of zinc metal will react completely with 75 mils of 0.2 molar sulfuric acid? So first thing we need is our equation. Let's see if I can make this so my hand's not in your way. So zinc plus sulfuric acid, H2SO4. It's going to react together. It's a single replacement reaction. So that means that my hydrogen and zinc are going to swap out. I'm going to have hydrogen gas, and then zinc is +2, sulfate is -2, so ZnSO4. And it's balanced, so that's cool. So we want to know the mass of zinc metal, so I want to know this in grams. Will react completely with, and then I like to write down my information given underneath the items that I have in my reaction, because it helps me stay more organized. So I have 75 milliliters of 0.2 molar HCl. So I always start with a measured quantity that I'm given. So the thing that I measured that I'm given is my 75 milliliters of my sulfuric acid. So I want to go from my volume, my milliliters of sulfuric acid, to grams of zinc. So I'm trying to find. So if I go up here, well, milliliters is a volume, and this is a solution. So I'm starting with the volume of one thing, and I want to get to the mass of the other thing. So I'm going to use stoichiometry to get there, because I have two of these, and I know my molarity, so I can get from volume to moles. I have my balanced chemical reactions. I can go moles to moles, and then I know the molar mass of zinc from the periodic table, and I can go moles to mass. So let's do that. So I'm going to start with 75 milliliters sulfuric acid, and you can draw a fence or you can draw your times and your fractions. I need to get 2 liters because molarity is moles per liter. So there's 1,000 milliliters in a liter. Then liters drops down, and I'm going to go to moles, H2SO4. And this is where moles per liter, that's my molarity. There's 0.2 moles for every 1 liter. Then I go moles to moles. So moles, H2SO4, moles of zinc, and that is a 1-to-1 mole ratio. And now moles drops down, grams on top, and according to periodic table, 65.39 grams per 1 mole. I've not done these calculations ahead of time, so I don't have my cheat sheet with my answers. So if I make a calc error, you can come tell me tomorrow. So I get 0.98 grams. 0. And I start with 3 sig figs, my measured value. So I want 0.98. And then after that is a 0 and an 8. So I'm going to do 0.981 grams of zinc. All right, so that is one of the new things is just using molarity to convert between moles and liters of a solution. All right, something we have used before is using molar volume when we have gases. So this asks us to calculate the mass of ammonium chloride. That's this one, NH4Cl. So I'm looking for the grams to produce 11.6 liters of ammonia gas. That's this guy. 11.6 liters of gas in the reaction. So I'm going from 11.6 liters of NH3, and I want to find grams NH4Cl. So volume of one thing to grams of another. This time my volume is of a gas, so I'm going to use my 22.4 liters per mole to get to moles, moles to moles, and then moles to grams. So another 3-stepper. Starting with the measured value I'm given, 11.6 liters NH3. I'm going to go liters, NH3 drops down from liters to moles of NH3. Then moles of NH3 drops down. I'm going from moles of one thing to moles of the other. So moles NH4Cl. Then moles drops down again. And now I'm going from moles of one thing up to grams NH4Cl. So here is this one, liters to moles. So 22.4 liters per 1 mole. 22.4 liters per 1 mole. Mole to mole is my ratio. I have a 2 in front of ammonium chloride, a 2 in front of ammonia. And then this is my mole ratio. Let's see, nitrogen's 14.01, 4 times 1.01 for my hydrogens, plus chlorine is 35.45. So I get 53.5 grams. So multiply across the top, divide by the bottom, 11.6 times 1 divided by 22.4 times 2 divided by 2 cancels out, times 53.5. And I get 27.7, 3 sig figs to start, so 27.7 grams NH4, you too, Cl. Oops, there you go. Now you can see it. All right, 2 down. A million more to go. All right. Next, we can use stoichiometry to calculate limiting and excess reactants. So this is a review from Chem last year. We have sulfur and chlorine reacting to the equation below. If I have 202 grams of sulfur reacting with 303 grams of chlorine, this should be a little 2 in the reaction below. Oops. What is the limiting reactant? What mass of product will be produced? What mass of the excess reactant will be left over? So I want to know my mass of this guy, my product, my sulfur hexachloride. So 2 stoichiometry setups, grams of one to my grams of product, and the other one, grams of my other reactant to my grams of product. So 202 grams sulfur. Sulfur is what? 32.06 grams per 1 mole. Moles to moles, there's 1 mole of sulfur for every 1 mole of sulfur hexachloride. And moles to grams, 1 mole sulfur hexachloride is, great question, 32.06 plus 6 times 35.45, 244.76. 244.76 grams sulfur hexachloride. 202 divided by 32.06 times 244.76, 1,542. And I'm going to keep all those sig figs for now because I'm comparing to start. So next, 303 grams of chlorine, and it's diatomic chlorine. So that means that my molar mass is 70.9. 30. I did it in my head. Yeah. Good. 70.9 grams of chlorine for every 1 mole of chlorine. Then my mole to mole ratio, 3 moles of chlorine for every 1 mole of sulfur hexachloride. 1 mole sulfur hexachloride, 244.76 grams sulfur hexachloride. We can see that this is going to be smaller already because of this guy. 70.9 divided by 3 times 348.67, so 349 grams sulfur hexachloride. But took the computer off the table. Okay, so now that we know that this, the smaller amount made, at the time 349 grams of sulfur hexafluoride is made, my chlorine is gone. I've run out of it. So this is my theoretical yield, which is made by my limiting reactant. So all of this is my limiting reactant, because if I had way more chlorine, then it wouldn't be. So I can't just say chlorine is my limiting reactant. It's dependent upon how much I have, which means this guy, my sulfur, is my excess reactant. So limiting reactant is my 303 grams of chlorine. Mass of the product produced, that is my 349 grams of sulfur hexachloride. Excess left over. We can use the law of conservation of mass to help us with that. So I'm starting with 202 plus 303. So I'm starting with 505 grams of total product. I have used up my chlorine, so that goes to 0. I've used it all up. And I've made 349 grams of product. So the amount left over, because I just have 2 reactants and 1 product, 349, is 156. 156. So I have 156 grams, because I made 349. I have 156 grams of my excess reactant left over. So left over 156 grams of sulfur. Okay. What if a student only collects 300 grams in a lab? Percent yield. Percent yield is just like your percent on a test. It's what points you got divided by how many you could have got times 100. So her yield, which is the experimental yield, divided by the theoretical yield times 100. So her yield, 300, divided by, theoretically, she should have got 349, but we never do in a lab, times 100. 300 divided by 349. So she's got 4 sig figs there, 3 sig figs here, so we'll round to 3. So it's at 86.0%. Not bad. Percent yield. All right, so most of that should have been review. The next one, combustion analysis. So this was something we learned new in Unit 0. That comes up again because it's more reactions and stoichiometry with reactions. So we'll go through it again. So for pentanoic acid is analyzed by combustion. We have a 0.3 gram sample, produces 0.579 grams of carbon dioxide. Man, that should be a little guy. And this guy can get a little there. And water. Acid contains only carbon, hydrogen, oxygen. What's its empirical formula? So first, I like to write the reaction. CXHY, and it's got oxygen, so OZ. And it's combustion, so we react it with oxygen. And I make combustion reaction, carbon dioxide, and water. I have 0.3 grams sample. I make 0.579 grams of carbon dioxide and 0.142 grams of water. So if I figure out how many moles of carbon came out of this guy, those moles came from my carbon here. And if I figure out how many moles of hydrogen came out of my hydrogen that I made, those can only have come from here. And then with a little subtraction of mass, I can figure out how much mass was made by my oxygen, and then I can figure out my formula. So let's do our carbon first. So 0.579 grams carbon dioxide. The molar mass of carbon dioxide is 44.01 grams per 1 mole. And in 1 mole of carbon, there is, carbon dioxide. There's 1 mole of carbon. I guess we can go to grams. And for every 1 mole of carbon, there's 12.01 grams of carbon. I'm going to set up my hydrogen 2 right away. So my 0.142 grams of water. Water is 18.02 grams for every 1 mole. For every 1 mole of water, I have 2 moles of hydrogen. And for every 1 mole of hydrogen, now this isn't diatomic hydrogen, it's just atomic hydrogen. I've got 1.01 grams of hydrogen. So, let's see, 0.579, see that, times, so 0.158 grams of carbon. Point 0.0159 grams of hydrogen. So that means that in my total of my sample, my 0.3 grams, I did not leave you guys enough room on this, sorry. If I subtract off my carbon, 0.158 grams of carbon, and then I subtract off my hydrogen, 0.159 grams of hydrogen, I will be left with my mass of oxygen from this guy. So 0.3 minus 0.158 minus 0.1, that's a 0. 0.0159. I get 0.1261 grams of oxygen. Okay, now, so that was the first part. Now I need to do my empirical formula of my 4-keto-pentanoic acid. Remember, for empirical formulas, I take my grams of each to moles, divide by small, multiply till whole. I'll squeeze that in over here. Should have given you guys way more room. I'm so sorry. So carbon, 0.158 grams of carbon, 12.01, 1 mole, 0.0159 grams of hydrogen, 1.01 per 1 mole, and 0.1261 grams of oxygen, 16 mole. Just might squeeze this in. So 0.132 0.157 0.158 0.0788. Divide by small, so my smallest value is this guy. That makes this 1. 19.9, which is basically 20. It's a big thing. 0.0132. Well, ain't that fun. Did I mess something up? It's just a weird number. It says experimental data, but 1.66. Oh, that's an icky number. So that's 0.66. Let me just check my notes. I don't want to make sure I didn't do this right. This is what happens when you do things on the fly. What task is this? Molar volume, limiting reactant, percent yield, combustion. Oh yeah, I'm right. Why did that get 2? What did I drop? Guys, I dropped a 0. Dropped a 0 on this one. 0.0159 divided by 1.01. That makes more sense. I was like, that was weird. Guys, I messed up. That gets a 0. Divided by 0.00788. So that makes more sense. Good. That's 2 less crazy. 2, 1. Okay. So if I have a 0.66, I need to have a multiplier that gets that to a whole number. So 0.66, like 0.33, means I multiply by 3. So what I do to one, I have to do the other. So times 3, 2 times 3 times 3. So that means 1.66 times 3 is 5. So C5. 2 times 3 is 6. H6. 1 times 3 is 3. 03. Did I get it right? Yes. Got it right. Oof. That was a big one. That was a big problem. But now you know. Okay. Next one, hydrates. Remember, a hydrate is a water molecule that's been incorporated into solid structure. These are usually ionic compounds with water molecules attached to it, and we name them as hydrates. So like if we had this guy here, this guy is cobalt 2 chloride, and then there's just one water molecule here, so we say hydrate. If I had more than one, whatever the number was is a prefix, like di, tri, tetra, and so on. So we need to figure out what the prefix is that goes here for our hydrate in this question. So the anhydrous salt is the ionic compound with the water removed from it. So we have a sample of hydrated salt, copper 2 chloride with some number of hydrates on it. The mass of 11.3 grams is heated to drive off the water of crystallization, cooled and reweighed until constant mass of 6.41 grams is achieved. So this is another empirical formula. I have my hydrate of 11.73 grams. My anhydrous salt is just the cobalt 2 chloride without the water with it, which is 6.410 grams. So the difference between the two of them is the water that was removed. So 11.73 minus 6.41. So 5.32 grams of water. So I want to know what's my molar ratio of cobalt 2 chloride to waters to get this multiplier here. So 6.41 grams cobalt 2 chloride. And you get its molar mass. And 5.32 grams of water. So 18.02, 1 mole. What's cobalt? 58.93 plus 2 chlorines, 35.45, 129.83. 129.83 grams per 1 mole. 6.41 divided by 129.83. 0.04994. We'll go one more decimal. 5.32. You guys will see my calculator. Divided by 18.02. 0.295. We divide by small, so we divide both by this guy, which makes sense. We always want it to be per 1, so it makes sense that this is the smaller one. So 1, this guy divided by 0.0494. 5.97, so basically 6. 6. So my formula is cobalt 2 chloride dot 6 H2O, which we write that cobalt 2 chloride. 6 is hexa, so hexahydrate. All right, a couple more to do. Next, we have titrations, and we talked a little bit about titrations last year for most classes, unless it was COVID, then we didn't. But titrations have to do with acids and bases, and we can do titrations without acids and bases, but classically we do them with acids and bases. One of our units later on, I think it's 7 or 8, one of them, is all about titrations and acid-base reactions. So we'll spend way more time with that then. For now, we'll just do a little brief overview of what acids and bases are, and some stoichiometry we can do with neutralization reactions and do that here. We'll get into more of it later. So a refresher, acids, remember they start with hydrogen, right? And they're going to donate hydrogen ions. This hydrogen ion is going to get donated in aqueous solutions, which means bases are the opposite. They're going to accept that hydrogen ion, and once they accept it, then they react. We can do a titration, which is an experimental analysis that utilizes the concentration of solutions, where we take a titrant, the solution of known concentration, is what we do a titration with, a titrant, and we analyze an analyte, which is the solution of unknown concentration. So an analyte is analyzed by a titration using a titrant. So the words go together. We do a titration until we get to the equivalence point, where the concentration of hydrogen ions equals the concentration of hydroxide ions, which is a stoichiometric ratio. And we like to use some sort of indicator that has a color change, which is called an endpoint, at the same place where we have the equivalence point, because that's what we're trying to find. So if the color changes there, then we know that we've gotten there, because we can't see the molecules. We have strong acids and bases and weak acids and bases. Strong acids and bases completely ionize. So they completely break apart into their 2 ions, and this reaction is going to hang out on the right side of the reaction. So if I have water with hydrochloric acid, which is a strong acid, my hydrogen from hydrochloric acid is going to get donated, right? Acids donate hydrogens to the water. I'm going to make H0 plus, which is a hydronium ion, which we usually just abbreviate as H plus, because we'd get rid of the other spectator ions in here. And then the chloride would be left by itself. If I had a strong base, so if B is my base, that's going to accept a hydrogen from water and become BH. So the hydrogen ion is going to go there. And then I'm going to have my hydroxide ion left by itself. But I totally have now ions. Oops. I have ions in solution. So it's important to note. I completely ionize. If it's weak, there's very little ionization. And so we have this double arrow here. And that double arrow means that, well, some of it's going to break apart into ions, but a whole lot of it's going to stay over here. This. I'm going to stay over here on the right side of my equation. That's where I'm going to hang out. because not much of it actually ionizes. Now, if I have an acid and a base, especially if I have a strong acid and a strong base, what I can do is I can neutralize my acid with my base. And when that happens, the hydrogen ions from my acid react with the hydroxide ions from my base. This is the acid. This is my base. And they make an ionic compound, which we call a salt. An ionic compound. CMPD is compound. And I make water, H2O, or I like to write it as HOH because it's way easier to balance. All right, well, let's look at a reaction between a strong acid and a strong base. I have potassium hydroxide, KOH, and sulfuric acid, H2SO4. This is a strong base. It's going to completely ionize in solution and be aqueous, as will my strong acid of sulfuric acid. Eventually, you'll have them memorized, but for right now, I'm just going to tell you if they're strong or they're weak. They're going to react together. My hydrogen and my hydroxide are going to get together, and my base part, my B part of my base, and the end anion of my acid are going to get together to make my salt. So I'm going to have K2SO4, group 1 metal, so that is aqueous, and water, HOH. And water is a liquid, okay, not aqueous. You can't dissolve water in water. So this is my regular reaction. Complete ionic reaction. I'm going to break apart all my aqueous things. Liquid stays as one. So potassium ions. Oh, did I balance this? 2, 1, I had 2 here. 2 there, 2 there. Okay. So 2 potassium ions plus 2 hydroxide ions, aqueous, plus 2 hydrogen ions, and a sulfate ion. Sulfate's -2, aqueous. And my products, 2 potassium ions plus my sulfate ion, 2. And water, not aqueous, so it stays as water. I'm going to write it as H2O because that's water. Okay. Spectator ions cancel out. So potassium, potassium, hydroxide, no hydroxide, hydrogen, no hydrogen, sulfate, and sulfate. So then I rewrite whatever is left over. 2 hydroxide ions plus 2 hydrogen ions make 2 waters. And because they're all 2s, you can drop those out. They can cancel out and reduce. 1, 1, and 1. So I have my hydrogen ions, which is my acid. My hydroxide ions, which is the part of the base that does anything, makes water. I have that there. With our neutralization reactions, we can, of course, do stoichiometry to find out quantities about them. So hydroxides can be used to neutralize acids. It is found that an indicator changes colors at the precise moment that 44 mils of sodium hydroxide has been added to 25 mils of 0.2 molar HCl in a titration. Calculate the concentration of sodium hydroxide. So first we had a reaction. Sodium hydroxide plus hydrochloric acid makes sodium chloride and water. Already balanced because they're all 1s. I have 44 mils of NaOH to 25 milliliters of my 2 molar HCl. Calculate my concentration. So I want to know its molarity. So to know its molarity, I need moles per liter. I know my volume because that's milliliters, so I know that, but I don't know moles. So it means I have to find my moles. I'm looking for my moles of sodium hydroxide. So that means my known value, 25 mils of HCl, is my known measured value, and I'm trying to find my moles of NaOH. So all this is stoichiometry. I head on back here. I know volume of a solution. So that's here with this guy. And I want to find moles of my other one, of the sodium hydroxide. So 2 steps. So 25 milliliters HCl. From milliliters, we're going to convert to liters because we've got molarity, right? This is moles per liter. So 1,000 mils, 1 mole, nope, 1,000 milliliters for 1 liter. Now, 1 liter of HCl and our moles, we want to get to moles of HCl, and I have 2 moles of HCl per 1 liter. That's my molarity. Now I can go from moles of HCl to moles of sodium hydroxide. And it's a 1-to-1 ratio. It's 1 mole of HCl, 1 mole sodium hydroxide. This is the last one, guys. So 25 times 2, right? So 50. I need 50 moles of NaOH. So if I want the molarity of NaOH, molarity equals moles per liter. I said I have 50 moles. My volume, 44 mils divided by 1,000 is 0.044 liters. Seems awfully concentrated. Oh, I forgot to divide by, you guys, I forgot to divide by 1,000. Yikes. It is a Friday afternoon. Okay. It's also when I wish I used pencil. 25 divided by 1,000 times 2.05. That makes way more sense. I was like, holy concentrated base. 0.05 moles. 0.05 moles divided by 0.044 liters. Let me give us a much more reasonable number. 1. What do we got for sig figs? 3. So 1.14. 1.14 molar NaOH. Whew. So, long story short, what should you do? That's the last page, right? Yep. If you have a chemical reaction, write the reaction. Write what's given to you underneath, and then consult your Motropolis, right? Your stoichiometry chart. Do I know one value from one side? What am I looking for from the other one? Do I know conversions get there? Do I know molarities? Do I know molar volume? Do I know molar mass? Do I have a reaction? And then use that to get there. Thanks for hanging in there today. I know it was long notes, but lots of explanations. And then we'll practice a whole bunch of precipitation stoichiometry in class tomorrow.